we're diving deeper into our stiffness and our displacement equations and better understanding them so that we can apply them in our example video next time for shear walls with openings. And yes, Jose broke a window and we still haven't fixed it. Let's get into it. We remember that stiffness equals force over displacement. Today's video, I am getting rid of the F to denote force and using V to represent story shear. And then something I haven't talked about in previous videos is the rigidity of our wall, which is really the same thing as the stiffness of our wall. They're kind of used interchangeably, in my opinion. But rigidity is equal to a unit load of 1 acting on the wall and displacing it X amount. And so what that does is that unit load is unitless, so it's not kips or pounds or anything like that. It's just a force of 1. And what that ultimately does is breaks down the rigidity of a shear wall into a decimal. And then if you were comparing rigidity of multiple different walls to one another to determine the distribution of the diaphragm forces to each of your vertical lateral elements, you would use this decimal of each one of your shear walls, sum them up together, and then divide each individual wall's rigidity decimal over the sum to get the percentage of distribution of force to each one of your shear walls. We will be doing that, not in this video here today. This is the primer, in my opinion, today to wrap your head around getting to that next step. We're looking at a cantilevered shear wall. We've talked about this before. This is our equation here in order to get our total displacement. If you don't remember, head back to my previous videos. And I did learn in my studies that there's actually another variable. This is the third part of the equation. And this contributing factor takes into account rocking of your shear wall and uplift of your foundation, contributing to more displacement of your wall. So if we had a footing down here and that footing were to pick up as this thing tries to overturn, that rotation is going to increase the amount of displacement of your wall. Through my research and through my studies, I have been told, or I'm seeing, that this is more of an intensive process to take this additional portion of the equation into effect, or into consideration, at least for hand calculations. So with that, we're going to ignore it today. But if you do want to know more about it, it is there. It is something that can be considered. Talk with your principals, your project managers, you know what to do. Let's reduce this equation down to something a little more simplistic so that we can use it later in determining our shear wall deflection for walls with openings. Just a little quick background. I was gonna put some numbers to the variables, but it's actually not needed. Just remember, E sub m, the modulus of elasticity of masonry, is 900 F prime m. I believe it's different between clay brick and concrete brick, so just double check on that. And then a shear modulus, which is for masonry only, equal to 0.4 E sub m. So this is, if you have a change of material, this is going to change. This is only for masonry is there this relationship. Otherwise, you got to get into Poisson's ratio and go through that and find G, because G is actually the thing that's supposed to be right there. So just don't just jump to conclusion on this one. This is only specifically for masonry. We drop a variable because E sub V, it turns into a comparison of E sub m. That gets us this. If I stop erasing everything, that gets us this. And so what we can do is pull out from the denominator your modulus of elasticity of masonry and carry it over to the other side of the equal side. So that gets us the following. And additionally, since we're going to be following this rigidity equation, we can swap our V, or our story shear, for just a unitless 1 as I stop erasing everything. And that's going to leave us with this equation here. We have our moment of inertia I and our cross-sectional area A. If we took a a plan view or a bird's eye view looking down at the top of our shear wall, we would see something like this. Remember, the force V is acting at the top of the wall from page left to right. It's pushing on it. And so the wall is wanting to rotate about its center axis as dashed here. So the reason I bring that up is because your moment of inertia is dependent upon the way with which you're rotating about your geometry. That means that our equation I equals BD cubed over 12 for a rectangle, B is going to be T, and L is going to be D, which gets us the equation over here. And then the cross-sectional area is simply your thickness T of your wall times the length of your wall L. That gets us this right here. We clean up our first part of the equation. We bring that 12 up to the numerator, and then we do 12 divided by 3. That leaves us with a nice clean 4h cubed over TL cubed. And then the shear deformation portion of the equation just kind of stays pretty relatively the same, 3h over TL instead of over A. Next, we see that we also, like we did with the modulus of elasticity, can pull out a thickness from the denominator and bring it over to the other side of the equal sign. Next, a big kind of, I'll call it a variable, but a ratio for our shear walls. The height of your shear wall and the length of your shear wall is something that's very critical and drives a lot of the calculations for altering stiffness of your shear walls. So we're going to keep that ratio within the parentheses, and we're going to kind of pull out the other values just so it's pretty clear as you start to mess around with your shear wall how it affects the performance of the wall. So H over L we're going to throw into parentheses. This is an important note. If all of your walls have the same thickness and they're built of all the same material, aka your modulus of elasticity is the same for each wall, then we can reduce this equation further because both of those terms now just equal 1 and can be stripped out. So we cross these out because they're both 1. And then lastly, we know that rigidity of a shear wall is equal to 1 over displacement. And so that gets us rigidity equal to 1 over our entire equation. Now, this is for a cantilevered shear wall. So in comparison, if I leave K as V over delta and rigidity equals 1 over delta, we went from this original stiffness equation to this rigidity equation. I know I'm using stiffness K and rigidity R, but they are in essence exactly the same thing for this type of calculation. Well, this is for cantilevered shear walls. But what about if we have, because we are going to need this for next time, what if we have a condition where we have a fixed shear wall? Well, I'm going to scroll us back up here, and you'll see. So the only thing that changes is your flexural portion of your equation, which is this right here. And instead of a 3, this is a 12. But everything else about the equation stays the same. So if we walk this all the way through, let's see what happens. So this is 12. So this is 12. So that's unchanged. We move down here. This is 12. 12 over 12 is 1 instead of 4. So that goes to 1. That goes to 1. That means this goes to 1, which in essence just goes away. And so for a fixed condition, R, make sure I'm not in the way, it's going to be equal to 1 times H over L. So a pretty easy walkthrough to see to compare the differences. And next time we'll use both equations to solve our displacement of our shear wall with a hole in it.